I know you guys have seen these formulas in the shop, but I want to go over where they come from for you. We're going to look at cutting speeds. And really, when you're looking at cutting speeds, all you're looking at is a velocity. Something has to be moving at a certain speed in order to do that. So there's two things that can move. Either the tool can stay stationary and the piece moves. This would be turning on a lathe. And there you're looking at a circular object that is moving. Or it could be the piece is stationary and the tool is moving. Now, you're not going to move the tools fast enough in a straight line, at least not with the equipment that you guys train on, in order to do any sort of significant cutting. So there's something, what's turning there would be a mill. The bit is turning, and that is spinning and penetrating the material. The other possibility would be possibly a drill press, which very, very similar, but because of the fact that not only are you spinning, but you're also going longitudinal to the rotation, it works just a little bit different on the drill press. For both of these, the actual surface is the spinning surface is the speed of the cut. On the drill press, it's spinning, but it's also going into the material, and that is the speed of the cut, is the rate at which it's going into the material. So we're going to look at mostly turning and milling for right now for our examples. So if I'm looking at something that's on the lathe that's turning, what affects how fast a point on the surface of that material is moving? Because remember, our tool comes in and that tool is stationary. So the cutting speed is the rate at the surface is moving. Well, RPM, of course, affects. RPM stands for revolutions per minute. So if it's moving 600 RPM, it is going around 600 times per minute. So this point will pass that tool 600 times per minute. That's not the whole story, though. What else do we need to know how fast that point is moving? What's that? No, feed rate doesn't really matter. Diameter. The bigger that circle is, the further that point has to move to make one revolution. In fact, how far is one revolution around this? It's the circumference of a circle, which is found by pi times diameter. Pi times radius squared would be area. That's your circumference. So those are the two factors that determine how fast that point is moving. The RPM and the circumference of that round piece. And again, circumference you can just consider it to be the diameter. So the speed at which that is moving is pi times the diameter times n, which is, n represents the RPM. One problem here, though. The diameter would normally be measured in what units? Inches. We normally measure speed in feet per second. So we have to convert this from inches to feet by divided by 12. So your surface cutting speed, which we use C for that, is your cutting speed, is equal to pi times your diameter of the piece in inches times the RPM divided by 12. I said diameter of the piece, but it could be the diameter of the piece or the diameter of a milling tool. So let's say that we have a 1.5 inch round piece of stock in a lathe, and it is spinning at 400 RPM. Let's find the surface cutting speed. What am I going to put in here? Pi, 3.14, yep. Times 1.5 times 400 divided by 12. Good. So 3.14 for pi times 1.5. I could very easily convert that to a decimal, so I'm going to do that to make it easier to enter here. You guys most of you have a fraction key on your calculator, so it's not a big deal. Times 400 divided by 12 gives me 157 feet per second. Now in the shop, you don't necessarily use this formula, do you? You use a shortcut formula. It's 1.5 times 400 over, it's like 3.87 or something. 3.82, is that what you use? Do you know where the 3.82 comes from? 2.62? Yeah. That doesn't make sense. 3.82 sounds better. Do you know where the 3.82 comes from? Right here. That's just 12 divided by pi. Is all that is. So just taking that out and making it one factor. I leave them in there just so it makes more sense as to where it comes from. If you use that in your formulas, that will give you the right answer every time. It's just a little shorter is all. Well, let's look at a little bit different situation. Now we have a piece of stock that we're going to mill a groove into. We want this to be a 3/4 inch groove. And our mill is going to be set to run at 325 RPM. What's going to be the surface cutting speed here? Tell me what to do. Pi. Just one pass, yep. 0.75 times 325 divided by 12. Good. So 3.14 for pi times 0.75 times 325 divided by 12. So 63.78. Usually we round to the nearest one, so we call that 64 feet per second. Not so bad? Try it, see if it goes in right. Now, most of the time, we're not trying to calculate the surface cutting speed. Most of the time, we know what the cutting speed has to be because you know what kind of tool you're using and what type of material you're cutting. And if you know those two things, you look up in your machinist handbook, your machinery handbook, and it tells you what your surface cutting speed needs to be. Most of the time, you're going the other direction. You know your tool, you know your diameter, you know your cutting speed. You have to figure out what RPMs you're going to set that at. So let's say that we are going to operate a mill. Did you get done what you needed to, Jason, there?
Yeah.
Right. Let's say we're going to operate a mill, and based on the materials we're using, we need a 200 feet per second surface cutting speed. We are cutting 5/8 inch diameter piece of material. We need to know how many RPM to run that at. Well, if we were looking at that, our formula, C equals pi dn over 12. Which one of those variables represents the RPM? N. We need to solve for N. Now, we could just put these numbers in here and solve this equation, but this is one that we're going to do often enough that it'd be nice to rearrange this equation to make it a little simpler to use. So I'm going to solve for N. I'm going to do that by first getting rid of the 12 by multiplying by 12 on both sides. So we now have 12 times C equals pi times D times N. And now if I'm getting N by itself, I have to get rid of pi and D. They both multiply N. So I'm going to divide by pi D. Cancels them out. Dividing by pi D on the other side, all I end up with is N is equal to 12C divided by pi times D. Now again, you probably did 3.82C divided by D. So for this particular case, we go back up here. We have a 200 foot per second cutting speed. So that's 12 times 200 over 3.14 times 5/8. So as I'm putting that in the calculator, 12 times 200. Now we have to be careful here. Bless you. I can't just hit divided by 3.14 times 5/8. I have to do divided by and then parentheses 3.14 times 5/8. Why did I need those parentheses? Well, remember, this line across here, that fraction bar, is an enclosing symbol. It's telling us we have to do everything on top first and then everything on bottom. And then we divide. So by putting that parentheses around that, I'm telling the calculator that it has to multiply the pi times the diameter first before it divides. That gives us 1,223 RPMs, it looks like. That might be just a little fast. Well, 200 is a pretty hefty surface cutting speed. Yeah. 200 would be for aluminum, and only if you have a pressurized coolant for aluminum. So let's do another. I'm going to have you guys try one. Tell me what would be the RPM. How many RPM would you run if you need a surface cutting speed of 120 feet per second on a mill that is a 1 1/4 inch diameter mill? Find the RPM for me. So here we're going to get RPM is going to be 12 times 120 over 3.14 times 1 1/4. Now again, when we punch this in the calculator, I'm going to put parentheses around that just to make sure it works out. 367. Let's see how you come out. So we got the 12 times 120, which would be our 1,440, divided by, put parentheses around, 3.14 times 1.25, close those parentheses, 367. Get a gold star. Made your day.
So much easier to do it the other way.
When you just use the 3.82.
Yeah, 3.82 times the surface speed divided by the diameter.
Then you don't have to worry about the parentheses. And that would work out the exact same way. If you did.
When I said earlier about the surface speed,
Yep.
well, using that, I was right. Using the .262.
Yep.
As long as you round up, it's going to give you the same answer. On when we were figuring out surface speed.
Okay. If you did the 3.82, you don't have to worry about parentheses, and you get the same thing, 367.
Round up.
Just slightly different. This was 366.87. This is 366.72.
And when you're
one
dealing with
RPM is not.
Yeah, that's not.
Chances are you're going to round that up to 370 or down to 360, 365 anyway.
Yeah.
Well, the next thing we want to look at is cutting time. What this is, it can apply to a lathe a little bit, but it's mostly to a mill. Let's say you have a piece of material, and you're going to mill a groove across that material. So we're going to call this the length of our cut, capital L. We want to know how long it's going to take to get across there. Well, we need a couple of things we need to know. One thing is the feed rate. What is a feed rate? Well, a feed rate is, on a mill at least, the feed rate is how far that tool can advance into the material for every revolution of the bit, of the tool. Sound familiar? Inches per revolution. Generally, it's like 4 thousandths or 3 thousandths of an inch per revolution. So we're going to call that F. That's our feed rate. And then we would need to know our RPMs, the number of revolutions. If it's turning faster, if you have 200 revolutions per second, you're going to advance twice as fast if you're only turning at 100 revolutions, or revolutions per minute, not revolutions per second. So the first thing we need to figure out is how far do you move in a minute? The distance you would move in a minute is going to be the feed rate, which is your distance per revolution, times your RPM, which is your number of revolutions. So that's your distance. Well, the time it takes would be the length of that cut divided by how far you would move in a minute. The time in minutes, of course, we're looking at. Be the length of that cut divided by that feed times the RPM. So let's say that we are making an 8-inch cut across there. And we're going on a feed rate of 0.03 of an inch per revolution. And we've already figured it out, and we are turning at 410 RPM. So let's figure out how long it's going to take to make this cut. So we have 8 over 0.003 times 410. Now again, if you're putting this in your calculator, anytime you have more than one thing on the bottom of that fraction, what do we have to remember to do? Parentheses around it. Very good. So this is 8 divided by parentheses 0.003 divided by 410. Close. That can't be right, can it?
No.
I sure hope not. Let's try that again. 0.003. I divide instead of times, that's why. There we go. 6.5. That sounds better. What period of time is that 6.5 in? That is minutes. Not inches, just minutes. Just minutes. Well, 8-inch cut is pretty hefty cut. I mean, 0.03 per revolution is a small advancement, but if you're going through a steel, that's not off. So let's put this all together in one big example. Let's say that we have a 3/4 inch milling tool in a material where we can run a surface cutting speed of 120 feet per second. And we need to make a 6-inch cut. Let's figure out how long this would take. Well, the first thing we need to figure out to get the cutting time, we need to know RPM and length of cut and the feed rate. Oh, I gave you the feed rate yet. We're going to use a feed rate of 0.04 of an inch per revolution. So again, we have to, in order to get the cutting time, we need the RPM.
When you're doing that, the 4,000s per rev.
Yep.
Now for us, is that our like chip per tooth?
Yeah.
Okay.
Yeah, if you've got a 2-tooth or a 3-tooth.
Gotcha.
Yeah. I'm just simplifying it by not, getting into 2 or 3-tooth.
It's laminated.
You got yours all ready in your wallet, right next to your blood donor card. So anyway, the first thing we need to figure out, RPM. So we're going to find the RPM by doing what? 12 times the cut rate over pi times the diameter. So 12 times 120 divided by, remember putting the parentheses, 3.14 times 0.75. And there we go. 611 RPM. What do we do with that? Now we figure out the cutting time. So 6 inches over 0.004. I'm going to actually put the units in there this time. Inches per revolution times 611. RPM is revolutions per minute, like this. You'll see when I multiply the feed rate, 0.004 inches per revolution, and the 611 RPM, revolutions cancel out, and this becomes inches per minute down here. Well, then the inches and the inches per minute, well, the inches will divide out, leaving us just minutes. So we'll punch this in. 6 divided by 0.004 times 611. 2.45. Well, let's take this one step further. Let's say that you are asked to bid a job, bid the labor time for your shop. And the task that you are going to bid is just your portion of the task. You are milling a groove again. This is going to be a 4 1/4 inch cut on a piece of material where you're only going to be able to use a 90 foot per second surface cutting speed. A feed rate of 0.03 of an inch per revolution. Again, that's taking into account the number of teeth on the tool. Excuse me. And you're using a 7/8 inch diameter mill. You have an order for 200 parts. You estimate that you can unload and reload the machine in 1.5 minutes. So that's per part, 1.5 minutes. How much labor time do you need to put into this bid for this particular task? So we need to find the cutting time of cutting that groove. Where are we going to start? Okay, so we're going to find the RPM by, what do we put in here? So 12 times 90 over 3.14 times 7/8. So I'm going to put this in the calculator. 12 times 90 divided by parentheses. 3.14 times 7/8 is just 7 divided by 8. Close my parentheses. Equals 393 RPM. Where do I go with that? I have my length to cut, 4.5. My feed rate of 3 thousandths. What am I going to do? Perfect. My length of 4 1/4, 4.25, I'm going to put it in as, over my feed rate, 0.003 times 393. So 4.25 divided by, parentheses, 0.003 times 393. Close. 3.6 minutes. Now what do I need to do? I'm going to add 1.5 minutes to that. So 1.5 minutes, that gives me 5.1 minutes. Is that for the whole job? That is per part, per piece. So then we have to buy 200. So that means 1,020 minutes. Divide by 60 because we're probably going to bid this one in hours. So yeah, it's 17 hours you're going to put in there. Almost 3 whole days. Where are you working at?
That's one shift.
I've had several days where that wasn't even my
God.
full shift. Now, of course, in our modern times, more and more of our stuff is going metric. Since we've got to deal with China and all those other competitors, actually there are several large corporations now that have gone totally metric. IBM is one of them. IBM does all of their, even their U.S. manufacturing is done completely in metric units. They figure it's saving them hundreds of millions of dollars a year. Because otherwise, every time they did a design drawing, they had to have all their dimensions in inches and all their dimensions in millimeters or meters, so that parts can be produced overseas and come mesh with parts that are produced in the United States. And also, they had problems because sometimes the conversion between metric and standard wasn't perfect, and some of the parts that were manufactured in foreign countries came here and they didn't exactly match up because there's round-off errors and stuff in the conversions. So, well, more and more companies are going to strictly metric. Standard units are going out the door. The larger the company, especially if they have an international division, the more likely it is that the metric units are going to take over. I can guarantee you the United States will go metric at some point. It just may not be in our lifetime. You're counting on it? You're hoping to outlive it? I was told when I was in middle school, which was a little over 25 years ago now, that boy, within 10 years, the United States is going to be on the metric.
You remember when they did that big push?
Yeah.
Yeah, they did that big push for a while and tried to make everything metric.
They even have all the road signs that were kilometers and miles. And all the cars, actually for a while in the late 80s, a lot of the cars, the main units were kilometers and miles were in the small units underneath.
Yeah, my digital.
Just push the button and it switched.
My LinkedIn, it goes back.
Mm-hmm. So anyway, how does this all differ if we're dealing with metric? Well, not a whole lot. The only thing that really differs is our cutting speed formula. Well, it's pi times diameter times your RPMs, but in metric, the cutting speed is not measured in feet per minute anymore. It is measured in meters per minute. The diameter will not generally be measured in, anybody remember what units usually measure diameter of tools in, or diameter of a turn piece? Millimeters. We're used to using centimeters because centimeters are closest to our inch, but outside of the United States, the centimeter doesn't get used very much. It's usually millimeters and meters are the ones that are used. How do we convert from millimeters to meters? Divide by 1,000. So instead of dividing by 12 to go from inches to feet, we're dividing by 1,000 to go from millimeters to meters. So let's say we have an 18 millimeter bit, and we are turning at 500 RPM. Find the cutting speed. Well, our cutting speed will be pi times 18 times 500 over 1,000, which gives us 28.26 meters per minute. Now you look at that, that seems really small, 28.26, but you got to remember there's like 3.2, 3.3 feet in a meter. So that's the same as about 93 meters or feet per minute. Well, again, usually we're not concerned about finding the surface cutting speed. Usually we have the cutting speed given and we're concerned about finding the RPM. So let's say that we know that we want a cutting speed of 35 meters per minute. And we have a piece of material that is 30 millimeters. Find the RPM. Well, we're just using the RPM formula. N is equal to, but instead of 12 times the cutting speed, it'll be 1,000 times the cutting speed. over pi times our diameter. So 1,000 times 35 divided by, we still got to remember our parentheses, 3.14 times 30, close those parentheses, 371 RPM. What do you think? I can just see the energy oozing out of this group today. Oh yeah. Here's some more. In the packet I passed out on page 242, 1 through 57, the odds. Deal with this stuff. This unit, by the way, is a really short unit. We'll finish up most of it this week. Probably have a test on it sometime early next week.